Let's discuss a question from fluid mechanics. So what is asked is, on one side you have water which is in not viscous and incompressible, and it flows at a steady rate of 3 meters per second. And on the other side you have a very large cross-sectional static mass of fluid, and the head of that is driving this water towards the right. So basically we need to find this depth h. So basically, because of this column of water, we have a pressure created here, right? And that pressure is certainly greater than the atmospheric pressure at the right side. So because of that, there's a flow towards the right. So what we will do is, because there's a flow, we apply the Bernoulli's equation at level 1 as well as at level 2. Level 1 is where at the interface between the static fluid and the this interface basically, and 2 is at the right side location. So we apply the Bernoulli's equation between 1 and 2. Okay, so depending on the term I'll explain you. Okay, so once I apply Bernoulli's equation, P1 by rho g is my pressure term, v1 square by 2g is velocity term, plus z1 is the potential head term, and p2 plus by rho g plus v2 square by 2g plus z2. Okay, now for potential head z1 and z2, I need to fix a reference datum for these calculations. So this is my datum for z1 and z2 calculations. So let's see how the terms apply. Now P1 is the pressure that is acting at this interface, and because the above fluid is static, so in a static mass of fluid the pressure increases by the term rho gh. Okay, so this is atmospheric pressure. So what I can do here is, P1 will be the atmospheric pressure plus rho gh. Okay, now remember that this is water, but I don't know what is the layer above it. Okay, this I don't know. This is some liquid, some alien liquid which I don't know. Okay, okay, so this is rho g. Okay, P1. Okay, now rho g is specific weight, and the specific weight of that liquid is given. So I'll write Pa plus Wh, right? Because W is given for that liquid. And what is v1? V1 is 0 because it's very larger cross sectional area, so the velocity, the change in level, the rate at which level changes will be 0. Z1 is 1.2 on the left hand side. Okay, and now on the right hand side, P2 is basically atmospheric pressure, V2 is given as 3 meters per second, and Z2 is 1.5 meters. Substituting all that, what we get is Pa plus Wh by, now this rho is of water because the fluid which we are considering, we are applying the Bernoulli's equation, is water, plus v1 square, v1 is 0, plus z1 is 1.2 is equal to P2 is again Pa by rho g plus velocity is given as 3 square by 2g, which is 9.81. Okay, plus z2, which is 1.5. so Pa by rho g on the left side, remember that we are applying for the water, so Pa by rho g on the left and the right would cancel. You will be left with the Wh by g into rho of water plus 1.2 is equal to 3 square 9 by 2. So 2 into, so we have everything. We need to get h, and W is given as 7.85 kilonewton, so 10 power 3. H is there, and then the density of water is 1000 into G, which is 9.81. so this 1000 and this 10 power 3 gets cancelled, so you are left with H on the right side and everything you have in numbers. So when we calculate this is just a substitution problem. Okay, so 7.85 h by 9.81. So you can simplify, you only have h. So what we get is, after simplification, 0.95 meters. So 0.95 meters of that liquid head is required to get velocity of 3 meters on the right hand side. So the answer is, in meters, it is 0.95 meters. So this is just an application of Bernoulli's equation. Remember that Bernoulli's equation, when you have all these composite fluids like one above the other, you have fluids, apply Bernoulli's equation for one fluid. Keep in that mind. That will simplify the problem. Thank you.